Today is a very technical webinar on applying loading to MasterFrame. It will be quite fast paced and will be in three parts. We'll first of all look at basic loading on members in MasterFrame, simple frames, plane frames, trusses, the likes. And then we'll look at the area loading, the part that you get inside the MasterFrame Pro. And finally, we will look at the adding in of the wind loads. I put together this little table for you before we started, and it basically talks about what types of loads you have. So obviously self-weight is handled in MasterFrame. Member loading is in MasterFrame, nodal loading, equivalent notional horizontal loads or forces, depending on your BS or Euro code. That's all MasterFrame, and even P delta analysis, which is really a form of loading. That's all in the basic MasterFrame. Once you go to MasterFrame Pro, we can add in our gravity loads and our self weights of slabs directly. And then with the wind analysis, we can add in our wind loading. What we will not be covering today is the finite elements and dynamic and seismic loading. Those are specialist loads. So this isn't going to be a PowerPoint or a Word document presentation, but there are some important things to understand. So what I'm going to do is minimize that, and I'll come back to that little document and start up MasterSeries 2017 from the 23rd of January. In fact, I believe there's an update to it. And we're just going to go into basic frame loading and look at some loads. Now the frame has got an unusual bit to the side, and there's a reason behind that we'll see in a minute, but just ignore that member at the start. So turning on loading, I haven't loaded the frame up everywhere, but I have put some loads on. So if I was to come in and look at the loads, these are member loads directly applied to the members. And I go to member loading, and I look at an individual load member. We will see we have two uniformly distributed loads, which have a total, when we factor them up to the Euro code, of 27. We also have a partially distributed load between 2 and 4 meters, which is here. And we then have some point loads. You have 2 point loads here and here. And if I just zoom in, you'll see that. But interestingly enough, as well as that, we have a high point load at the end of the member. We'll talk about that in a moment. And then I've repeated that elsewhere. But what I want to look at is the individual application of a load on a member. We used to have a whole lot of loads down here, but now we find that these three loads cover most instances. So let us look at this member here. So we're going to just zoom in on this member, and I'm going to add a UDL, and I'm going to add a UDL that is 10 kilonewtons per meter run. Now I'm just temporarily going to go to my load diagram, and we're going to go for all loading cases, so they're unfactored loads, and then back to my editing. So my 10 kilonewtons per meter run is 10 kilonewtons horizontally, so it's on the horizontal projection. It's a y-axis load, and we can handle x, y, w, z, n, and m. X and y are pretty straightforward. We look at our coordinate system. X and y are vertical and horizontal. Z will be into the page. So what's the W load? Well, the W is a special load that really only comes into play when you have very, very sloped members. So that is now measuring the 10 kilonewtons, but measuring its intensity along the length of the member. So I have a member that is 10 by 10 coordinates, so 14.4 meters in length. So you'll see that the W load gives me 14.14 as my total intensity per meter, because it's converted it by the slope. Whereas normally we work with an x-axis load, which is over here, just drawing it in this direction instead of over here. A y-axis load, as we thought, and even a z-axis load, which is along the member, but it's still only going to be 10. So that's out of plane and hard to see in this case. So that's your basic load directions. The W is this weight, this self-weight, which is very useful for dead loads on sloping members. Personally, I would never use it unless your members are at a slope of greater than about 7-8 degrees, because less than that you're under 1% variation in load. Obviously density we handle separately, and they're always measured per linear meter of member. We then have these two special directions, normal to member, and if I just increase the value of this to say to 50, we can see that this is coming on the underside and it's perpendicular, so it is pushing it up perpendicular, 50 kilonewtons per meter run. So this is like a wind load, and if I was to turn around to make it a positive wind load, it would then be pushing down on the member in its major axis. N for normal, and M is the minor axis normal, so it would have been pushing along this into the page. So if I went and changed it to an N and put it into 3D and rotate, you would see that it's now applied to the normal side of the member. So that's important to learn, that you can that loads are measured per horizontal length for X and Y loads, but we do have the W load. So I'm just going to kill that load. There it is. I'm going to put a partial UDL. So horizontal direction is 10 meters. So I'm going to go from 2 to 8. It's actually going left to right because of the direction of the member, and I'm going to go 1. So we get again 2 meters and 8 meters out from the node 1, and if I renumbered the member it would switch that round, renumbered the frame. So again, this partial UDL or partial trapezoidal load is measured per meter run. The third type of load is the point load. And the point load, because it's normally measured along a member, is actually measured along the slope of the member. So that is actually measured down here along the slope. So it will be 7.07 to get it at the midpoint. So the point load is the only one that's measured along the length of the member, because it is just a finite value. Now, I also mentioned about additional loads. So you can apply density here, but there's no need. These 5 loads here, 6 loads, are old-fashioned loads which are no longer needed. So I would highly recommend you ignore these. So I'm going to just forget about this member now, and I'm going to come up to my roof. And if you look, we have introduced a couple of new values. We've introduced a spacing. So this frame spacing, this allows me to take my loads per meter run and make them into loads per meter squared. So I have 1 kilonewton over a 5 meter width gives me the multiplied up value of 5. And I have 5 times 0.6 gives me 3. 5 and 3 is 8 kilonewtons per meter. Now, The other load that's very useful in here is the torque. So I'm going to add in a torque. At the minute it has no effect. I'm just going to move that up in the list. So now it's going to have an effect on both of these loads because they come after the torque in the list. And I'm going to say that we are 150 millimeters. That means if I put my frame into a 3D view, it's actually going to, and I just rotate a wee bit more so you can see it here, it's actually going to apply the load at 150 millimeters away from the shear center. We can also, for horizontally applied loads, give you a Y eccentricity as well. So if I said 300, we could push it up above the member by that 300. And I'm just going to put that back to 0. Now, the one trick about this torque to understand, and I'm just going to add another torque in, is that it would apply to all loads until you tell it otherwise. So what I would do for good practice is say that this dead load of 1 is applied eccentric, whereas the live load isn't. Naturally, in this case, this example, with the frame spacing, that doesn't quite make sense because you would be multiplying it up by the value at the same time. But where you do have wall loadings, the torque is a very useful tool to actually get that. With this example, if I was to apply a dead load that was in fact, so take this, move it up, add in another UDL, move that up, make that a dead load. So just highlight it and go D and make this. Now, if I have an 18 kilonewton per meter run or a 15 kilonewton per meter run wall, I would have to input it as 3 so that it multiplies it up by 5. But that is offset, so the wall load is offset and the rest are all concentric on the frame. Okay, so that's that one. These again are not used. They're old-fashioned point moments. These two are rare but are available. Coefficient of thermal expansion and a temperature rise. So you can define a rise in some of your members in temperature to see what forces are trapped in. And then finally, we move along and we can see we have this last one called short, which allows us to define members short of each other. So what I'm going to do now is looking at manipulating the loads. Again, let's forget about that. So zoom out to the full frame, window, forget about that all to the left hand side. There are two important aspects. One is that every load has a load group, D1, L1. And interestingly, D2, L2. Well, D2, L2 does not mean it's in the second span. That is because I want to have this maximum when this is minimum, max, min, max. So by separating the loads into 2 groups for dead and 2 groups for live, then we can do this because we can activate them separately. So a load group, what is a load group? Well, looking at my little document, I extracted 1 or 2 things out of the manuals. And load groups is basically any set of loads that are applied at the same time. So in this portal, the dead loads are both the uniform and the 2 service hangers. Or you could have put the 2 service loads in a D2 group, so you could do it without or with. But more importantly, if you look at the wind load, W1 is blowing on the side as a partial UDL, normal, normal and partial, and there are 4 different intensities, but because they always occur at the same time with the same load factor, they're in the one load group. So very simply, that's how we manipulate our loads. So what I want to do is to take this load here, and I'm going to take out the ones that I don't want and that I was playing with, take out the torque, take out that, and I don't need a lack of fit. I'm now going to take these 2 loads and I'm going to apply them to create a pattern load. So what I can do is I can go to copy, and I can say put it onto here and put it onto here, because they will be D1s, L1s, D1s, L1s, D1s, L2s. Because I'm in copy mode here, I'm going to quickly change over to 2 and 2 and then copy that to there and there. So very simple. You can use this copy mode as a palette to put things on. Now, if I wanted to come and take some of these loads and put them onto these other two members, but I didn't want the parcel or to distribute it, I would go to the member, go to copy, so I'm now in this thing called copy mode, and I would just kill the bits I don't need. It's not removing them from that third member, it's just saying what members have the same load, and I am going to apply that to that member, and I could change it then to be a D2, L2, and apply it there. Likewise, we have the third option is the global option. So I can say global, and I can look at a pattern of loads, and here we highlight all the members of the same loading, and I could change that from data 4 to data 4.8, and then I could go to its alternates and replace it there as well. If I look down here, because I have distinct other loads, when I go to global I only get the one member, and it can be quite disconcerting to have the one member. In fact, I tell a lie, it's two members, but you also have the ability to copy or modify a single load. So if I wanted to take the point loads that are here, I could modify that such that it is not there but somewhere else. So I could then take this partially distributed load and reduce it, change its value just on these two spans. So that is applying loading onto the members. The next stage is I want to now look at nodal loading. Now, I put this load here on as a load at the end of the member, but this one was not a load at the end of the member. And it's quite important to understand the difference. Because that load is on the end of the member, so if we look at the member loading again very quickly, member loads, and we can see this 200 kilonewton load at the 6 meters on my 6 meter long member. Any shear that comes from that will go directly into this beam and will shear this beam. Whereas this load, which is a nodal load, will go straight into the node and be dispersed between any members that can support it, such as the column and anything in here that's going to take it, but it's not. It's going to go straight into the column. So it's a great way of getting rid of that shear, but obviously the real answer is it is how you construct it. If the load comes in from a beam coming in a third dimension onto another beam, then you put it in as a beam load. If it's coming into the column, you would put it in as a nodal load. So if it's coming into the web of the column, put it in as a nodal load. Now, nodal loads are very, very, very easy. So under loads, we have nodal loading. And I come down and I look at, and I'm just going to turn off nodes. I've just got this nodal load at this point, which is minus 200 on this node. And again, I have set it onto the D1 load group. So you can apply loads very simply. And if I create another group, I could put a load there. Sorry, I just closed that by mistake. Put the node there. And I could say that it's an FX load of minus 200. So there comes a horizontal load. And in fact, it's in the same group as this one. So I have messed up. So I left that node in, put that node back there, so it's 200. I also have the facility to rotate that and I can say that I have a point load at a rotation to the horizontal of 45. So it's now going to resolve that on plan, or in the vertical plane it could be at 45, which gives me that minus 45 means that the load is coming down in this direction. So it resolves it externally, but internally it stores it as that. So we can put on moments and shears or nodal loading if we so desire at inclinations to help us. So that's your nodal loading, and it's very simple to get through from it. The next item, before we move on to area loading, the real crunch of the whole system, is loading cases. So let's look at loading cases. And I have some basic loading combinations set up. These basic combinations are for the all spans loaded, alternate 1 where you have maximum and minimum, alternate 2 all spans loaded service, and then repeat. And you'll notice I'm using D0 as well. It's common to use D0 for your self weight of your members, although to the Euro code you'd be perfectly happy using it in D1 because you never pattern your permanent loads anyway. And these loading cases are very simple to set up. You can just come in and type them in. You go to a loading case and you add a case, and then you go and you put in the values either through the buttons or through typing yourself. And that's how you generate them. But you don't really have to do that these days. If I go back to the cases, there is an option to auto-generate or update all cases. And this uses the intelligence that we have in the system so that we can turn around and say we want dead and live, live load only, dead load only, dead plus live plus wind, dead plus wind. And I can say that I want for each of these to use 610 rather than A and B. So I don't want to have the 1.25 and 1.05. I just want 1.35 and dead and wind. And then we can say what parameters are included in each. And the other thing we can do, and it's most important to look at it, particularly for the dead and lives, to say we want to include equivalent horizontal notional forces, the new word for notional loading that you use in the Euro codes, and we'll choose it as per the wind loading direction. So we'll come, and in fact we will actually override that and say no, 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 because it's a plane frame. We'll just go for 0 and 180 on those. And that allows you then just to go and generate the cases. Very straightforward. We now have 18 loading cases. Only 18 because we didn't have any wind loading in this frame, and we'll see that again when we move into area loading. So let us come out of this little frame that we were playing with and look at area loading. And the great news about area loading is going to be that for 2018, when we release the 2018 version of the software, people who are using PowerPad will get area loading. So, typical frame, steelwork, and it has got on plan some interesting areas. This is an interesting area, and so is this. Some fantail options. If we look at it on front view, sorry, full frame front view, you'll see that we have something up top, and that is a little portalized sort of orangery roof light system for the internal core that is open. So to keep it nice and clean, they've put a roof over the top. It saves all that extra work and hassle and keeps it all nice and sheltered throughout the year. So that's my little frame. So we're now going to not put members on directly, or so loads on one at a time. We're going to put loads on the areas. So loading, not member, not nodal, not notional, not density, but floor and roof panels. So default loading, let's go for the defaults. And it's going to come in and I'm going to turn on area loading. And it's going to say, yeah, we're going to take the coordinates and build up a list of levels for you. So we've got levels here, 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 here. In fact, here and here as well, but we'll not worry about that too much. So level 1 is at 3.5. So for each level, we can set up a whole list of information. So for level 1, 2, 3, so 1, 2, and 3, I can turn around and say that we have a 1 kilonewton superimposed dead load. I'm not worried about self-weight. We have a live load of 4 and we have a slab thickness of 200. So that is going to take 4 plus 200 times 24. So we better tell it the slab is 25. In fact, I think to the Euro code, or is it 26? 26 for heavily reinforced. For lighter reinforced, we'll go for 24. And that has now been applied to all of those. Level 4, which is the roof, and there's no reason why we can't call it roof. We're going to have a superimposed dead load of 1. In fact, I'm going to keep this light. I'm going to go for 0.5 and 0.5, and then we go for a live load of 0.6. So it's going to be a lightweight roof, and we're going to have no slab thickness, so it's just going to be that. So these are my default setup, but I haven't got any loads on the frame yet. So closing that down and closing that down. It's quite nice just to come back out to wireframe in black and white, and I will just go for wireframe. So what I want to do now is to go into my levels. As you can see, the levels have all popped up there, and I want to go into, say, level 1. And here I go. I don't need to see the grid lines, it just makes things a wee bit more cumbersome. And what I want to do now is to do my area loading. So walking down, and I want to add panels. So give it a name. First floor. In apply mode, select everything we want to include, and then take out anything we don't need. So that's atrium all the way up. You'll notice that it gives us a default span. I can change that, or I can ask it to go shortest. So every time it's changing and chopping, which is probably not desirable, I am going to go for horizontally spanning for the majority of it, and then we'll maybe fix these and these in a second. So I can also say that I have an outer edge projection of, in meters, 0.5, and that takes the whole outer and gives us 500 mil projection and the area loading that comes with that. And we can even say that's from the edges of the members, so according to the size of the members, it'll keep readjusting that if we so desire. But in our case, and we normally don't, we'll do that. So we could override the dead and live load for this whole floor, but why would you want to? Because you've already set it. If you had two areas of floor that were totally different intensities, it would make more sense to actually create them as two separate groups. So if, for example, I was to come and say, let's take that out and just keep that one and that one, then I could do all these to the default and then increase the loading on these as I need to do and put them in as a second group. You can also use that for grouping in different directions. But what I want to do is to make a local panel change, and I want to take this member, so it's highlighting this one for me, and I want to change the direction to be vertical, Z, and then I want to copy that onto that and that. And I'm just going to draw the 3D because it gives me some clarity. So everything else is looking fine. So that's my loading on my floor. I can turn around and go to this area and choose this one. So, and I could say that I want to increase the live load to 6. So that has now got a different intensity, and if I say color, you'll now see that it's now a different intensity. So I can specify an intensity for one or two small areas. Naturally, as I said, if it was a larger area, you would do that as two separate groupages. Now, my last problem is all these over here. So if I take this, is going to be fine horizontally. These two would probably be best. So I'm going to take this one and I'm going to change the span to be perpendicular to that member, and I'm going to copy that to that one, turn it off, do the same over here, and I'm going to make this perpendicular and choose the member, that one, and then copy that to that one. So now I have fixed those all up. Rather than wireframe and you don't want full, you can actually just go for slightly thicker lines, and that gives you the definition so that you can see what you're doing a lot clearer. I'm experienced and I knew what I was doing. Now, no floor is without additional loading. We have two types of additional loading, line loads and patch loads. If we go to loads, you will see that we also have line loads and patch loads. Interesting, we can also do edge projections on individual members, which is quite useful. So if you want one side to have a little projection, but in this case I want to put some line loads on. So we define start and end in two directions referenced to a member. So let's make this simple. We'll choose this member here, this red member, and we get up to 4 different load types. So we're going to say 18 is my dead load. I could change that to live if I really wanted to, but it's going to be dead. So nothing shows up other than it's there because it's over the full length. If I suddenly say it's starting at 1 meter along, I can do that. If I say it's at 18 meters, it cannot get outside the member because it's sitting on top of the member. Once I move it off the member, even by the tiniest of proportions, I can make it go along a length. But instead, I could then just say, wouldn't be necessary. You could just do that and say it's on that member and that member and then that member. So different ways. But in my case, I am going to go from the 2 meters to 18 meters, and I'm going to start at the 0, just put it in for reference, but it's going to come out by 5 meters. So it's coming along, but at this point it's out 5 meters. Totally nonsensical, but sometimes you get them. So we can put our line loads anywhere we want on the member. The other type is the patch load, and it's very, very similar. Let's put the patch load in as a 6 kilonewton live load, and we'll reference it on this member, and we'll say it's from 1 to 3, and it's from 1 to 3. So it is a 2 by 2 square panel. Now, one of the little tricks is that you're able to add a dummy member at any stage. So I could put a dummy member from here, and then I could move it in to wherever. So that little dummy member doesn't exist, it's only there. And if I change then this member not to be referenced to that, but to the dummy member, then it will rotate the orientation of the member to allow me to put it in as a rotated panel. So this member doesn't exist, it's there just for reference purposes to get my patch load rotated onto the frame. So now we would look at more floors, and my advice is that although you can go and have done the initial part, the area loading on all your floors at one go, I would highly recommend that you don't. And I need to fix that because that still thinks that's a physical member. I just need to go in and take that out and make it into a bracing member. So good point. First floor plan, and if you go for bracing members, you can tell it that that isn't a real member, and close that, and you'll then see when we put on the area loading that it ignores the member in the definition of the span of our floor. So I recommend that you don't just do them all in one go, but do each floor separately. It's a wee bit extra work, but it gives you so much more control over the application of your loading. Now the last thing in area loading, and yeah, area loading is quite quick to do. The last thing in area loading is if we need to do pattern loading because we have a rigid frame. If we have a rigid frame and we want, particularly in concrete, and want to do pattern loading, we would come back and we would look at the additional option of alternate patterns. And what that allows us to do is to say which members are, because at the minute we just told our area loading it's a dead load. We just told our area loading it's a live load. We didn't tell it anything else. We didn't tell it if it was D1, D2, D3. Well, the assumption is, unless you tell it otherwise, it's going to be D1. But if we wanted to do pattern loading on this, so we had a maximum, minimum, maximum, we would need to turn around and say, and in apply mode, that's a D1, that's a D1, and you could then do that, and that is D1, and you could do that as D1, and that is D1, and maybe even that as well, do no harm. And then you'd say your D2s are in fact the counter members, those, and in this case those. So you'll see now that your loads are separated. And if you think about it in the other direction, if you were spanning the other direction, if you were spanning onto these members, and it's only the members that have the load spanning onto them you actually have to put into these two groups. It's not like a flat slab where you need to have 4 definitions, your left to right and your front to back. In these you only need to have the 2 definitions to allow you to do your pattern loading. So it is quite easy to do the pattern loading. What's left in the loads menu? Bracing members we have covered. Bracing members just allow us to identify any member that is not directly carrying load and therefore shouldn't be used for framing up a load panel. And we will revisit that very shortly because we're about to look at that third aspect of loading, and that is wind loading. Wind loading is done using our wind analysis program. Without the wind analysis program, you could come along and define your wind panels and then physically put on the values of wind loading on to each panel in each direction. But that's not necessary. What I'm going to do is going to go through the process of creating wind on this. Now, if we look at this structure, we will see that we've got reentrant corners. We will also see, easier to see in 3D, when I rotate, I actually here have a balcony with a balcony, and this is at a lower level. I also have a canopy here. So that balcony is really that's a parapet handle there, and that's a little canopy with a tie holding it up at the corner to give it support. So those are the sorts of things that make this life a lot more awkward. So loading, very simple. Wind loading. Let's walk through wind loading directions. What are we going to choose? Well, yes, it would make sense to choose the 4 cardinal directions, and I will turn on wind program. Now, at this point in time, everything's okay. So now we walk forward and we look at wind load reduction on globally loaded members. What's that? Well, in the BS we had this A value where we could reduce the load on members that carried a lot of area of wind loading due to statistical reductions in the pressure. You don't do that in Eurocode, but you identify globally and locally loaded members. So that member's locally loaded, that member's locally loaded. These members here are globally loaded, the bracing. So what I need to do is to tell it what members are all my bracing members. So this is for the A value, not for anything else. And I'm going to turn around and say, and I'm going to go incline members only. And I am now going to, in apply mode, window all of those, and I think there's one other, not certain what that one's for, take that out, and I missed that one just in the zoom. So I've got all those members. I'm not worried about the portal frames because they're small anyway, so they are going to have the higher percentage. They're not carrying a massive area of loading, and that's that done. So the next thing is the site. So let's look at the site and choose a site. I'm going to choose a site over somewhere in England. I could just go in and say, oh, it's down there, and then say, well, it's roughly there. But I do have the national grid reference. And if I knew what that grid reference was, I could go and use it. Now, a great little program is called Grid Reference Finder. So if I fire up my Chrome, MasterSeries, UK Grid Reference Finder. So you type in your postcode, or you can say I want to go to Bath, and it takes you into Bath, and then you could come and more accurately, if you didn't know your exact postcode, say, well, yeah, it is actually near Alexandra Park. So we're going to put a new building beside this one. Just click on it and select the short grid reference, And for those who are not in the UK, you also have an Irish version of this you can link to. So all I need to do is paste that in, press enter. I'm now in Bath and I lock this down. So that's that locked down. The next stage in this first page is to orientate my building. I need to get my building orientation right. So I'm going to say that I want it to be coming with north in here. So I'm going to say minus 45 degrees. So now I've got my north coming in on that diagonal there, which means that this face here gets the worst load from the frame because it's looking at the topography and everything. You can also look at the topography and take the standard directional factors will reduce this a wee bit, but since I know my orientation, I will go back and use the full UK factors, which again shrink that back down so that it's not even before it looks at any topography. So that is the full value of wind. And guys, ladies, gentlemen, other than yep, it's Eurocode. Yep, everything else is all good. That's it. We just say, okay, done. Now, let's get back to our frame. And we'll just go for the wireframe and black and white. Now, what's next under wind loading? Oh, put the wind on the roof and the walls. That sounds sensible to me. So, do I have anything? No, I don't. I had been playing around, so a little title. I can come and say, right, this, and this are a wall panel. Can't get that one, can't get that one. They're not in the same plane. I can say it's vertically spanning or it's two-way spanning. And then I can come along and I can say, right, next, let's do this, and this. That is quite enjoyable. And I can say this one is single vertical spanning. So we now have two panels, masonry and some sort of vertical cladding system. And I can keep going and do that for all the different surfaces. But of course, it wouldn't be a computer program of any merit if it didn't have the ability to do it automatically. So I'm going to ask it to auto do all and see what it comes up with. So first of all, it's all in one color. Let's draw it in different colors for each panel so we can see that we've got different panels. And now let's start spinning around. And you'll see that we had set it to horizontally spanning. We can see the re-entrant corner. You'll also see that this is different to this because this is a parapet and that's not. Likewise for these. Spinning around and you'll see that we have this little canopy, although it does appear to also have its own little sub-member, which I'm going to kill because that's just a tie. So we've now got this little canopy. But we also have two problems around this corner, and these are ones I created on purpose. And these two problems are to do with one, this panel isn't very happy because it's trying to connect to the bracing member, and that is where in the menu you had bracing members or over here. So I can come along and say, actually, I want to add these two members to the bracing group. So that will rectify that problem and allow it to span accurately. So back to my wind loading. Surface. And in search mode, if I come here, there we go. And I then come along in apply mode and I apply that. But I haven't solved this other problem. What this other problem is to do with, we have a slight reentrant here that is glazed out and is not part of the primary building. But we need to create a corner in here so the wind can come in here and along here and along. So what we need to do is put in what we call dummy members. So first things first, put it into plan so I can see the frame. It is in here. So let's go and just drill down as little as we need. That'll get all the members I need to see. And come along, and I will see that I need to put member down, 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 and down to floor. So I can go right mouse click, add dummy member, and I can go from here to the floor, right mouse click, add dummy member, from here to here, right mouse click, add dummy. It just saves you having to come out to the full frame adding. And if I just rotate, I'll just do the same back down here, right mouse click, add dummy to there, right mouse click, add dummy from there to there, right mouse click, add dummy, right mouse click, add dummy from there to there. So that is going to allow me to frame this up. So if I go and I kill all my area loading panels, back out to full frame, and I now go auto, it'll trundle around, and this time when I get to the far side to here, you will see that it has, and I go for coloring it up, done it all right. I have to correct that thing again because it was just me. So if I go to that panel and kill, then everything else is now happy, and that's it all done for you. So that's the half. Now, because we now have wind loading, I'm going to revisit loading cases. So let's go back to loads, load cases, and let's go to the auto generate. So I got two cases at the minute. I'm going to ask for my dead and live to 610, and I'm going to take my wind directions, yes. My live load only is service only. Dead, don't know why I need it, but it's service only. Dead plus live plus wind is ultimate and service, so both of them to 610. And we're going to consider, and this is where the wind comes into it, the external overall and plus the internal suction and pressure, which is for the local members. Overall doesn't be affected by the internal suction because it's got a net effect of 0. So this is where those bracing members will be applied, and we also want to do the equivalent horizontal loads on those just to be correct, although I would argue that I've got a reasonable amount of wind, so I don't really need those. And I'm going to generate my loading cases. So off I go, and it's created for me 72 loading cases. As you can see, under Ultimate we're using 1.35, 1.5 and 0.9s, and we're also using with the 1.5s, and we're using the dead plus wind suction at 1.5 and 1. So all the loading cases and permutations are all there. So can I analyze this? Let's have a go. Static. Space frame. Is there a way of applying an axial load to a member, i.e. a pre-tension? Yes, there is, Catherine. Very simple. The point load I applied you can apply that along the axes of the member if you wanted to. You can also, if it's a pretension, add it in as a lack of fit. You can put in a 10mm shortening of the member to get that pretension, although you would need to do some mathematics to work out what is the degree of shortening to get the load you want. So yes, you can apply that as a load on the member, or you can apply a nodal load to do the same thing with a wee bit more control. Now I've analysed, let me see my results. Results I don't need, it's design I need. Let's go into design and steel member design. I'm going in here for a very good reason, because it's all really part of the loading, and it's the one thing I mentioned that we can do as a load in all versions of MasterSeries, and that's P delta. To do a P delta analysis, you really need to assess whether or not you've got sway stability in the frame. And sometimes it's set up automatically. In this case, I'm going to go in and ask for an elastic critical load factor. So now we have it looking at all the loading cases and seeing whether we need, and it's saying that our stability is only 2.1 here. That's low. They're all low, they're below 10, so suggesting that we do need to do P delta. And we just took it off the other cases for brevity, but we could put it on. So we need to do second order analysis. Second order analysis is really, to my mind, a type of loading, in that it distorts the frame and loads it. So grid line, full frame analysis, and it's second order analysis. So I can turn around and I can say that I want to do P delta. In this instance, we could go for the geometric stiffness matrix method, because we are primarily a static braced frame. But if it's portalized and the likes, and it's a better method, is the Newton-Raphson. So having checked that, that's going to apply to loading case 1, but I actually want to apply it, hold the control key down to all those and apply. So that would now do the P delta analysis to all of those loading cases. Is it possible to adopt the site data for countries other than the UK and Ireland? Site data, no. But we can still work out our coefficients and our pressures, because we don't have the altitudes or anything like that outside the UK. But what we can do is, if we go to loads, wind loading, wind site analysis, we come down here and under site, we don't worry about any of this. We just go to user defined queue, and everything else is irrelevant then. So we just set all that back to 1, and we then come back out, and then when we go into properties, and this is the one I need to find under wind, I think it's under wind directions. Yes, because we said we're going to use our user defined values, we turn around and input the pressure at each height. So he has put in a default of 1 kilonewton per meter squared, and I am going to say at 5 meters, that's it's in newtons rather than kilonewtons, 1050. At 10 meters, we're up to 1250. So that's just defining the heights, and we can actually do diagonal reductions if we're using the BS rather than the Eurocode. So between those two, we can now still see what the wind pressures are. So area loading, and it's not gravity, it is wind. And if I go for my W1s. Oh, I do need to do some other, there we go. We can now see we're using these values. So if I take the wind pressure in that direction, up here I am seeing a coefficient. The coefficients never change because they're just building shape orientated. The Q values are the pressures. So if I come down here and I can see that I'm getting 0.662, if I was to change this from 1200 to 1500 and regenerate, we should see that we are, well, of course my frame's not that tall. Let's manipulate some of these values again. So 1500, make this 1500, and just make this 1500. And there we can see that's gone up to 0.993, so it's gone up by 50%. So yes, you can input your own Q values and they will then be multiplied by the CP values, which is the CPE external plus any internal coefficients to give you the answers you desire. So overseas, outside the UK and Ireland, it is possible. So ladies, gentlemen from afar, I thank you all very, very much for attending and I wish you a goodbye.